Hi, this video is about wave speed. I remember back in 5th grade, I had this great teacher who taught me so many things about the world, and one of the things that she taught me was a little bit of science. And I remember sitting in class one day, and my teacher said to me and said to the class that sound waves travel better through solids than the air. And I remember thinking at the time, and I think I even asked the teacher, that why is it then that if I go into the hallway and try to listen to the teacher, I wouldn't be able to hear her through the door? Doesn't sound if sound travels better through solids, then shouldn't I be able to hear through solids better than I do through the air? And I don't remember exactly what she said, but I know I was very curious from then on. I just did not fully understand what she meant by sound traveling better through solids. And it wasn't until much later that I was able to kind of figure out what she meant. And that leads me to talk about the idea of wave speed today. So I have a slinky here that I would like to create some waves on. I'm just going to create some transverse waves like this. Let me get it all ready here. So we've got transverse waves here. And I want to see what I can do to make this wave travel faster. And I want to see what the speed of a wave depends on. So the speed of a wave depends on what? What can we do to make this wave go faster? Let's start by trying, probably one of the more obvious things to try is a higher frequency wave. What if we shook this slinky up at a high frequency? Would that make the wave go faster? So let's start by just a standard wave here. Okay, we're looking at how fast does the wave go from one end of the screen to the other. Now, what if I gave this a higher frequency? So instead of just my normal shake, what if I did a really quick shake? Does that make the wave go any faster compared to a slower one? If it does, it's not noticeable. So there's high frequency there, and then a low frequency one. Looks like it's going about the same. So it appears that the speed of a wave does not depend on the frequency. What about the amplitude? What if I give this slinky a really big disturbance? Would that make it travel faster? It would definitely have more energy in it. So I usually think, more energy means faster, right? So let's try it. I'll try a normal amplitude first. So same speed as before. Let me try a big amplitude and see if that makes it go faster. So it doesn't noticeably go faster, even though I do a big amplitude and a little amplitude, it still seems to go the same speed every time. So it appears that the amplitude does not affect the wave speed either. So what else is there to change about this slinky that would make the wave go faster? Well, one more thing that we could change is the tension of the slinky. What if I tighten it up a little bit? So let's try it again, normal speed right here. Now what if I took this slinky and I just stretched it a little bit more? Does this affect the speed? Wow, that's much faster. Absolutely. Let's go even tighter. Let's see. These waves are almost instant. These are a little slower, even slower. So it appears that the tension, now I'm going real slow, get it very loose here. Very slow wave. The one thing that does seem to make the wave go faster or slower is the tension. And more specifically, for not just a slinky wave, but for any kind of wave, the speed of a wave depends on what I call the snappiness of the medium. And I'm not sure if this is an actual word, but let's go with it for now, because snappiness is a good way to describe it. If you disturb something and it snaps back into place quickly, then that means the wave is going to move quickly through that surface or that material. The snappiness of a medium tells you how tightly bound the different parts of the medium are. So if you disturb one piece of it, the rest of it is going to, follow that disturbance and pass on that disturbance. So the snappiness of the medium will tell you the speed of the wave. And the snappiness depends on the tension, but it also depends on the mass of the medium too. So if I had a slinky that instead of being made of metal was made of plastic, but I put it at the same tension, the plastic is less mass. And so it's easier to accelerate, and it would probably go a little bit faster because of that, because it doesn't take as much force to get it to snap back in place quicker. So this is all that matters when it comes to the speed of a wave. And now we can go back to that original question, or that original fact that my teacher posed to me in 5th grade. And it starts to make sense. This is the speed of sound in solids, liquids, and gases. And I wrote the speed of sound over here in miles per second, not miles per hour. So this is very high speed. All of these are very high speeds. But you'll notice at the top here we have solids. These speeds are fastest. So sound travels about 4 miles per second through aluminum. So if you had like a 4-mile long piece of aluminum and you made a disturbance on one end of the aluminum, then that disturbance would travel at 4 miles in 1 second. Like that's how fast it goes, very fast. A little bit slower through iron and glass. But then when you get to liquid, water, it drops off, the speed drops off a little bit. It's only going about 1 mile per second at that point. So it's a little bit slower. And I think that's because we would agree water is not as snappy as solids are, right? If you disturb a solid, it snaps back in place basically instantly. You don't see it, get compressed unless it's like Play-Doh. If it's a solid, that bounces back up into place, you knock on a board like this, it bounces back up instantly almost. But liquids, on the other hand, they don't snap back in place as quickly, and so they don't carry a wave as quickly. And then even less so with air and gases, because if you disturb the air, it'll pass on the disturbance by bumping into other air molecules, but those molecules don't bump back into place as quickly. They're not as snappy as solids and liquids. So I think this finally answers the question that my teacher was trying to teach me back in 5th grade, that solids do allow sound to travel the fastest. So sound does travel the best through solids if we're thinking only about the speed of sound. Our ears, though, are built to hear sound in the air. Our ears have little air pressure sensitive air pressure detectors, and so we hear sound waves in the air the best because that's what we're made for. But sound does travel faster through solids and liquids. So that's all I've got for you in this video. Remember, humility is not thinking less of yourself, it's thinking of yourself less.